This video is on circle geometry, which is also known as Euclidean geometry. I'll be going through the different theorems with their relevant reasons and a little picture to understand what it would look like in a test or exam. So our first theorem is the radius and chord theorem, and that the line from the center would be perpendicular and the midpoint of a chord over here. So this line from the center meets the chord at its midpoint, which means it cuts it in half, and at 90 degrees. If they give you that it's 90 degrees, you can then say that this half is equal to that half. If they give you that this half is equal to that half, you can then say that the angle is 90 degrees. Generally, in a test or exam, they might give you dotted lines here, and you would have to calculate a side or something using the radius and Pythag. The reasons that you would use: line from center perpendicular to chord, and line from center to midpoint of chord, depending on which one you are using. Then, for the second theorem, this is the one which is angle of the center equals 2 times angle of the circumference. Basically what this is if you have a chord, for example, AC. AC subtends an angle at the center and an angle at the circumference. It means that the angle that it forms at the center is going to be twice as big as the angle it forms at the circumference. So this will be x, and this will be 2x. This will help when trying to figure out angles, and it's always nice to be able to identify the chord and then figure out which would be your 2x at the center and which would be your x at the circumference. Then we move on to tan perpendicular to rad. If they give you the radius and the tangent, we know that this angle will be 90 degrees. They can just tell you that O is the center and that this line is the tangent. You can then say, therefore, this angle is 90 degrees. In brackets, tan perpendicular to rad. Rad standing for radius, tan standing for tangent. A tangent is a line that touches the circle at one place only. The fourth theorem is when they give you the diameter of the circle. In this case, AOB is the diameter. The diameter is the line that cuts the circle in half. It is 2 radiuses joined together that cuts the circle directly in half. This theorem states that if this is the diameter and AC and BC are chords and each point touches the circumference, the size of this angle will be 90 degrees. You can then say, therefore, angles in a semicircle. That would be your reason for this. The next theorem, Theorem 5, this has got to do with angles in the same segment. If we look at AB, AB is our common chord. AB forms this angle ACB as well as angle ADB. So if you look at these two angles that it forms, they are the same size, these two angles, because they have the same chord and are both touching the circumference. It's very important that they both touch the circumference. The reason you would give for this is angles in the same segment, and you can use this to prove that angles are equal. We then move on to Theorem 6. This is when you are given chords that are equal in length. So in this case, AB is the same length as BC. And AB subtends angle ADB, and chord BC subtends angle BDC. Since AB is equal to BC, you can say that this angle is equal to this angle. I've illustrated it by saying x and x. They are the same size. Your reason would be equal chords subtend equal angles, which means the chords are if the chords are equal, they will produce the same angle. It's again important that these points are all touching the circumference of the circle, and that chords AB and BC are the same length. Then Theorem 7 is involving our cyclic quad. We have A, B, C, D, our cyclic quad over here. This theorem states that if angle B is x, angle C is going to be 180 degrees minus x. It basically means the opposite angles of a cyclic quadrilateral add up to 180 degrees. A cyclic quad being quadrilateral that fits perfectly into a circle. And the opposite angles, the interior opposite angles, will add up to 180 degrees. So for example, if angle B is 40 degrees, angle C will be 140 degrees. You would say 180 minus 40 to get 140 degrees. Then for number 8, we have the exterior angles of a cyclic quad. Again, we're dealing with a cyclic quad. Note that point A, B, C, and D are all touching the circumference of the circle. This theorem states that this angle will be equal to its opposite exterior angle. So if this is x, this will also be x. Basically, what I do to find the exterior angle, because it can be quite confusing, it's not this. If there was a line here, it wouldn't be that equal to that. You take a line, you draw a dotted line from the angle. So from A, we're going to draw a dotted line straight across to its opposite angle. And the exterior angle it forms outside of that would be the exterior angle that is equal to the first angle. So this would be x and this would be x. The reason, exterior angles of a cyclic quad. We then move on to the tan chord theorem. This is when you have a triangle inside of a circle and a tangent that touches the circle and the triangle at one point. The angle that forms between the side of the triangle and the tangent over here is going to be equal to the angle completely on the other side of the triangle. An easy way to find which angle inside the triangle it is to say, okay, here is the angle that I'm looking for on the outside. It's touching BC. So my other angle isn't touching here. So it has to be angle A. It can be a little bit difficult to know that it's angle A and not angle C. So just remember, if it is touching BC, then it has to be the complete opposite one at A. The reason for this, tan chord. We then move on to number 10. This is the last theorem, is when you have two tangents, like so. In this case, at point B and at point C, and they are the same length. So from AB and from A to C, they are the same length. Then this x and this angle x will be equal to this angle, also x. The reason, tangents from the same point. Because here's the point, and they are both tangents to the circle. Then this is just how you would find angles in a Euclidean question. Generally, what they would do is they would give you a big circle with a whole bunch of different lines, and you would have to go and find different angles and get them to equal, etc. So that is the first type of question you can get. What's important to do with that is to try and see what you can figure out is equal, by going through all your rules. So you can say, okay, can I use theorem 1? No. Can I use theorem 2? No. And go through your little list in your head to figure out what angles are equal to which, etc., etc. Okay. Those questions can be quite difficult. Hopefully I'll be putting out a video soon of an example of one of those types of questions. Okay. Then the second type of question you can get with Euclidean geometry is proving certain things. So firstly, you can be asked to prove a theorem. There are videos available on our YouTube channel for the different proofs of theorems. There is a CAPS one and an IEB one. So depending on which syllabus you're doing, you can go look at those. You can also be asked to prove that something is a tangent to a circle, and then what you would have to do is try to prove either tan chord or tangents from the same point. That basically means that you would have to try and prove that angle A over here is equal to this angle without actually using the tan chord theorem. So you can't use the fact that this is a tangent. You would have to use other reasons to make them equal, and then say, therefore it is a tangent because they are equal. You could have used tan chord now, knowing now that it's a tangent. So that reason you would have, therefore is a tangent, in brackets, converse tan chord. So you're basically proving it the other way around, if that makes sense. So you're saying that these angles are equal, therefore it's a tangent. So your reason that isn't tan chord, but rather converse tan chord. You could also use tangents from the same point if you wanted to. I just do think that tan chord is generally a more common one, but that doesn't mean that they can't ask you this one. Then they can ask you many other different things, like prove that the angles, like the lines are parallel, prove that one angle is equal to another angle. Then you can use these rules. As soon as they ask you, the last thing they can do is ask you to prove that something is a cyclic quad. You can't use the rules of cyclic quads, so you can't use rule 7 or rule 8 and say this is like, you can't say that A is equal to D, exterior angles of a cyclic quad, because you're trying to prove that it is a cyclic quad. So what you want to do is prove that A is equal to D. Therefore, they are exterior angles of cyclic quads because they are equal. Therefore, it can be. So what you would do is you would figure out that A equals angle D, say, therefore, it is a cyclic quad, converse exterior angles of a cyclic quad. You can use, in order to prove a cyclic quad, you can use, obviously, this one, Theorem 8 or Theorem 7. Again, you're only using it, but only saying it at the end. Or you can use angles in the same segment. So Theorem 5. Again, you can't say angles in the same segment until the end. And so you'll have to prove that these angles are equal in a different way and then say, therefore, it is a cyclic quad because they are equal, so therefore they are angles in the same segment, that type of a thing. You would again say, you would get that the angles are equal, say, therefore, it is a cyclic quad, therefore, they are angles in the same segment, or converse angles in the same segment. Okay. So once again, for proving cyclic quads, you want to try to prove that the angles in the same segment are equal, or prove that the exterior angles, that these angles are equal, therefore cyclic quad. Or number 7, prove that these two add up to 180, therefore opposite. Okay. And then once again, your tan, if they want you to prove that it's a tangent, you could try to prove that these two are equal and then say therefore it's a tangent, converse tan chord, or using Theorem 10. Another thing they could ask you is to prove that AOB is the diameter. You would then have to prove that that angle C is 90 degrees and say therefore AOB is the diameter. Converse, angles in a semicircle. So it's all about using what you know and applying it. Just once again, I know I've said this a lot, but when you are proving something, you can't use rules that you're trying of something you're trying to prove. So you can't use tangent rules if you're trying to prove it is a tangent. You can't use cyclic quad rules if you're trying to prove it is a cyclic quad. And you can't use diameter rules if you are trying to prove it is a diameter. You must prove it to be equal and therefore say it is a diameter. And that is all for circle geometry.